So when we're talking about writing net ionic equation, there's always going to be three steps. So the first step is the molecular equation. So do you remember when you're balancing chemical equations? That is the molecular equation. So the molecular equation is just you balancing chemical equation. That is the molecular equation. So like potassium chloride plus silver nitrate makes potassium nitrate plus silver chloride. Oh, how would we classify that reaction? If you had to classify this reaction, what would we classify it as? Is it a synthesis, decomposition, single replacement, or double replacement? Double replacement, right? So this is a double replacement reaction. And again, how can we tell? Because you have two compounds. And when you look at a double replacement reaction, so again, on your exam, you're going to be writing these. The K stays first. Whoever starts first, stays first. So do you see how the K stays first and the AG stays first? All that happens is these last two switch places because now the NO3 here and the Cl is here. So they switch places. So again, this is a double replacement. So a molecular equation is just like the equations you've been looking at all semester. Those are molecular equations. Now, the ionic equation, what we're going to do is we're going to separate everything that is actually an ion in solution. So in your homework, you had the questions of write the dissociation for, right? So if we were to write the dissociation for KCl, KCl actually comes apart into K plus and Cl minus. So what we're going to do is we're going to write the individual dissociations. So that's all that ionic equations are. So if we wrote the dissociation for silver nitrate, it would come apart into Ag plus and NO3 minus. Yes, you got to know those polyatomic ions still. If we were going to write the dissociation for KNO3, it would come apart into K plus and NO3 minus. But what about the dissociation for AgCl? AgCl is a solid. Do solids come apart? No, solids do not come apart. So the dissociation for AgCl, there is none. It does not dissociate. So when we're writing these net ionic equations, that's what you're looking for. The only things that come apart are AQs. So aqueous solutions, AQs are the only thing that comes apart. Solids, liquids, and gases do not come apart. So if we combine all that, so here's our KCl, here's our AgNO3, here's our KNO3, and then you see how the AgL stays together? This is what we call a complete or a total ionic equation. So that's a complete or a total ionic equation. And so again, all we're doing is we're taking all the AQs, and we're taking them apart, just like you did on your homework, that we're dissociating them. But if it's a solid, so a solid, a liquid, or a gas, it does not come apart. It stays together. Only AQs come apart. So this is a complete, again, or a total ionic equation. If you look online, everybody's got, some people, half the world calls it complete, half the world calls it total. So that's our total ionic equation. Now, to figure out our net ionic equation, do you see how the K's are exactly identical on both sides? And the NO3s are exactly identical on both sides? So what we do, and again, this one is our complete, also called total ionic. I'm just going to use both names because they really are used interchangeably. So what we do to get our next part is we cross off the things that are exactly the same on both sides. So again, the K is exactly the same, and the NO3 is exactly the same. And so what we have left is the Cl, the Ag, and the AgCl. This is our net ionic equation. So what's actually happening in the reaction? Oh, chloride ion is combining with the silver ion to create silver chloride. That's what's actually happening. And the things that we crossed off at the top here, those are what we call our spectator ions. So our spectator ions would be K plus and NO3 minus. They're spectators. Just like if you were going to watch a sporting event or a concert, you're a spectator. These ions, potassium and nitrate, are spectators. They're not actually involved in the reaction. What's actually happening here is this. This is the net ionic equation. This is the equation that's actually happening. So on your exam, you're going to get an equation, something like this. And it will say, well, you probably won't get the products. You might have to write the products, but it's what kind of reaction would we classify this as? You see two compounds, it's a double displacement reaction, right? So we'll work on those. And so then the next question would say, write the complete ionic equation, the net ionic equation, and identify the spectator ions. So every time it's the same steps. Everything that's an AQ, we break up. If it's not an AQ, we keep it together. So what are we going to keep together for this equation? See that solid? So that means this PbI2 does not come apart. Everything else comes apart. Okay, so when we see this Ki, this is going to come apart into 2K pluses plus 2 I minuses, because this 2 is going to go to the K and the I minus. Okay, when we look at PbNO3, it's going to come apart into Pb. So right when we were doing our dissociations, so this, I'm going to write it like you had in your homework. So this comes apart into 1 Pb2 plus and 2 NO3 minuses. Don't forget this 2 right here. So if I were to write this like and actually dissociate, it comes apart into 1 Pb and there's 1 NO3 minus. Here's the other NO3 minus. So if we combine these together, we make 2 NO3 minuses, right? And so when we do this, we just say Pb comes apart into 2 NO3 minuses. Okay, and then the same thing with our KNO3. Okay, so that's our molecular equation. And again, this is our solid, which again is called a precipitate, which does not come apart. So the precipitate does not come apart. So we break everything else up except for the solid. So here's the same thing. So there's our 2Ks, our 2Kis. Here's our PbNO3. There's our 2 Pbs, our 2 NO3s. And then we've got our 2Ks and our 2 NO3s from here. And you can see this PbI2 stays together. It does not come apart. So the PbI2 stays together. And again, this is our complete or our total ionic equation. And now when we look at this, what is exactly the same on both sides? Exactly the same. See the 2Ks? 2Ks, exactly the same. Anything else exactly the same? 2 nitrates. 2 nitrates. So those are our spectator ions. We cross those off and we're left off with IPB and PbI2. And again, our spectator ions are the ones we crossed off. So you will need to make sure that you can do this whole thing when you're doing your exam. And this is what your next homework is doing too. It's doing this. A lot of this. Okay. I want you to try this one. So this is exactly what your question would look like on your exam. It would look like this question. It would say, write the molecular complete net ionic equation and identify the spectator ions. So try this and then we'll go over it in just a minute. Okay, I'm going to help you with the molecular equation, right? Let's see how far we got. So here's our molecular equation. Oops, let's not write in yellow. So I'm just going to write it up here for you. So again, Na stays first because it's already first. Ag stays first because it's already first. The other two just switch places. So NO3 goes here and AgCl goes here. So we have to identify which one is a solid. That's another thing that we just did on our homework. Which one of these is a solid? If neither of these is a solid, we don't have any more work to do. We're just done. We just write no reaction and be done with it all. We really love no reactions. They're way less work. But how can we tell if one of these is a solid? What do we have to look at? Solubility table, right? And when we look at our solubility table, I always tell my students there's a couple things to always remember. All nitrates are soluble because nitrates are everywhere in our reactions and it's the most common one you're going to see, and they're always soluble. So if all nitrates are soluble, remember soluble means AQ. So if it's soluble, we write an AQ. So all nitrates are soluble. And chlorides are soluble except Ag, Pb, and Hg. So this one is our solid. So knowing that, so that's our first step. So knowing that, now we need to go and do the balance. We need to do the complete ionic and the spectator ion. So continue those and we'll go through them in just a Okay, so we split up all of our AQs for the next step. Okay, so for our complete ionic equation, again, it's complete or total ionic. It's kind of interchange. We separate all of the AQs, but not the solid. So this is going to come apart into Na plus. Now, all of these should say AQ after them, but I will not have enough room to write this. So these should all say, oops. It should say Na AQ plus Cl AQ. But I will not have enough room to write that on here. So just pretend everything says AQ except for solid. Now, I get the question a lot. Do I have to, this is Na. Do I have to do Na plus? Yes. Remember, the atom, sodium, is very different than the ion, sodium ion. Remember, what happens when we put sodium atom in water? We'll see this in lab. It lights on fire, right? What happens when we put sodium ion in water? Nothing. They are very, very different, right? So it is very important. This plus here that we're going to use is incredibly important. So Na plus Cl minus. We do need those charges. They are essential. Very different, right? That changing of that one electron makes a huge difference. Okay, plus, now we're going to do the same thing with AgNO3. Ag plus AQ plus NO3 minus AQ goes to Na plus AQ plus NO3 minus AQ plus, and now this is just going to be AgCl solid. And remember, don't take apart the solid. I think a really helpful thing to do is, do you see how I put that box around the solid? Put a box around your solid to remind your brain not to touch it. Once we decide what is the solid, don't touch the solid. Okay, so that's our complete ionic equation. We completely break everything up. The next step is the net ionic equation. So our net ionic equation, we cross off everything that's exactly the same on each side. So Na is the same, Na is the same, NO3 is the same, NO3 is the same. And so then we just take everything else down. So Cl minus, and now I have room, so I'm going to write the AQs. plus Ag plus AQ makes AgCl solid. That is our net ionic equation. It's pretty much the stuff that makes the solid. That's your net ionic equation. Now, our spectators, those are the things we crossed off. So our spectators would be the Na plus and, let's put a comma here, the NO3 minus. That's supposed to be a 3. Those are our spectators. So this is how we do our molecular, complete, net ionic, and identify the spectator ions for reaction. So again, on your exam, you're going to have one of these. You're going to have one of these. So you need to write the products, figure out what the solid is, write the complete ionic, net ionic, and then identify the spectators. And it's the same process. And you'll be practicing this in your homework a lot too. And there's some extra practice on Canvas where you can practice this in Canvas too. Okay. So now, again, this is just another, this is a type of double displacement reaction. We're going to look at another type of double displacement reactions. Maybe. Yes. So that's a great question. How do we know if it's a solid? So when you're doing a double displacement reaction, the first thing you need to do when you write these products is to look at the solubility table. And so we practiced the solubility tables last time, and you'll get a solubility table. I'll give you one in lab that you can use, and there's one on active that you can use also. And for your quiz and for your exam, you'll get to use a solubility table. So remember, you just need to figure out which ones are solid based on the solubility table. And we'll actually do this in lab too. So great question. Okay, so another acid-base reaction, or another double displacement reaction, is just called a neutralization reaction. Same premise, same exact thing, we just have a different name for it. So a neutralization reaction is just specifically between an acid and a base. But it's the exact same thing we just did, we just don't make a solid. Instead, we make a liquid. So this reaction right here, we're going to be doing this one in lab also, is an acid plus a base makes salt and water. So remember, a salt is just any ionic compound. So an acid plus a base makes salt and water. And remember from our nomenclature chapter, how can we tell if it's an acid? What does it start with? An H. So we already know acids. Acids start with H's. For our bases, we're going to find out our bases always end with OHs, with the hydroxide ion. So bases always end with hydroxides. Acids always start with H's for our purposes. Now, when you take other classes, you're going to find out there's a lot more definitions than this, but this is the ones we're going to stick with. Okay, so if we look at this, this is our acid because it starts with an H. This is our base because it ends with an OH. But if we look at this, this is just a double displacement reaction. Because if H stays first and Mg stays first, here's our Mg first, here's our H first, our Cl and our OH just switch places. So if I'm gonna write this here. So if our Mg stays first and our H stays first, and our OH and our Cl change places, that makes this a Cl and this an OH. Hold on. My computer's in doing what it wants mode today. So this is an OH. So if we rearrange HOH, that's just water. So it's a double displacement reaction, exactly like we did before. Same thing we did before. It's just this time, instead of a solid, we make water. Now this MgCl, what's wrong with this MgCl? We have to balance the charges, right? Because magnesium's charge is +2 and chloride's charge is -1. So we need to have a 2 here to balance their charges. That nomenclature is never, ever, ever, ever leaving us. So we need to balance our charges. And that's where we get the MgCl2. And so again, any ionic compound is called a salt. So metal plus a nonmetal, salt. So an acid plus a base makes salt and water. And this is called a neutralization reaction, but it's It's the same double displacement reaction we were doing. So let's try another one of these. Okay, so I want you to practice this one. Sulfuric acid and potassium hydroxide. So write the products of this reaction. And we're going to write the molecular, complete, and net ionic equations. Again, so remember when you write your products, if it's a solid, a liquid, or a gas, it does not dissociate. And remember, dissociate just means come apart. So write the molecular, complete, net ionic, and spectator ions for this reaction, and we'll go over it in just a minute. Yes. Okay, so we've got sulfuric acid and potassium hydroxide. So our sulfuric acid is, again, it's sulfate. Sulfate has a -2 charge, so we need 2 hydrogens, plus potassium hydroxide. So now, if this is a double displacement reaction, the H stays first and the K stays first, right? So if our H stays first and our K stays first, the other two just switch places. So HOH and SO4. Everyone see how I switched those two? So I just switched the OH and the SO4. So that's our first step, switch. Now we need to make sure all of our charges balance. Okay, do our charges balance? They do not, because SO4 is a -2. SO4 is a -2. At some point this will work. Negative. Every time I try to make a negative sign, it tries to go to the other side. Let me try this. 2, negative. Nope, there we go. Now let me make the negative sign. -2, and potassium is a plus, so we need to balance that out. So we need K2SO4. So we always have to balance the reaction and then balance the charges. Balance the reaction, balance the charges. Okay, now, write our products, balance the charges. Okay, so HOH just becomes water. Okay, is our reaction balanced? Do we have the same number of atoms on the reactants as the product side? Check out that potassium. Is it the same? It is not. So we need a 2 here to make that balanced. Now, all of these are AQs, except, is water an aqueous? Water is not. Water is a liquid. It's our only L, really, that we deal with in this class is water. Because aqueous means dissolved in water. Well, water is water. So it's just liquid. Okay, so this is our molecular equation. Our molecular equation. Now we need to break everything up into ions. So we're going to break everything up, but we don't break up solids, liquids, and gases. So are we going to break up water? No. Break everything up but water. So this H2 is going to become 2 H pluses plus an SO4 2 minus plus 2 K pluses plus 2 OH minuses goes to water stays together plus 2 K pluses plus an SO4 2 minus. This again is the complete or total ionic equation. Okay. Everyone see how I broke all those up? We're good on how the numbers come. And so then our net ionic is we cross everything off. That's exactly the same. Well, if we look, here's 2 Ks, 2 Ks, SO4, SO4, So all we're left with is 2H pluses plus 2OH minuses goes to H2O liquid. And then we just net ionic that. And then, oh, you can tell our balancing's a little off. I can see it. And this is our net ionic equation. Okay, what did we cross off? K plus and SO4, 2 minus. These are our spectators. Okay, so let me put this back so you can see our balancing is off. Here's where you can tell our balancing is off. 2, 2. Do you see how there's nothing here on this water? If when you're doing your complete and your net ionic equation, if the balancing of the ions doesn't work, do you see how this makes two, this is the too many oxygens here, this isn't working. That means that your balancing is off at the very beginning. So something's wrong in the molecular equation. What's wrong in our molecular equation? What are we missing? Is it balanced? So if we do that, then it ends up being balanced because we end up with 2, 2, and 2, and then we simplify it. And we end up with H plus OH plus water. Now that's going to happen a lot. If you misbalance at the beginning or miss something out, you'll see it won't work out perfectly. If it doesn't work out perfectly, that means you made a mistake in that top molecular equation. Oops, that top molecular equation, which is pretty common. It's easy to fix though. You have to go back and just check your balancing out. Okay, so these are neutralization reactions. So now we're going to look at a little bit of acids and bases. So we're going to look a little acids and bases now, but we're going to kind of really cover this in our acid base chapter kind of at our last week of class. So anything that reacts, that completely reacts a strong acid, we're going to find out, we call these strong electrolytes. That just means they make ions in water. So when we have HCl and we put it in water, it makes H plus and Cl minus. It makes 100% H plus and Cl minus. So that's what we call a strong acid, because we're going to find out acids are dependent on the amount of H plus we make, which we're going to talk more about later. Now, if we look at our strong acids, you do not need to know these, but I just want to show you that you know a lot of these acids. And again, they're all starting with H's. These are just some common strong acids that we use a lot. We'll be using those in lab. Now, a weak acid is very similar, except for a weak acid doesn't come apart all the way. Weak acids don't dissociate completely. Well, technically ionize, but we'll talk about that difference if you get to 219. They don't come apart completely. They only come apart a little bit. So for example, acetic acid, do you see how this arrow is different than this arrow? This one right here, this means a strong acid because it comes apart 100%. When you see this arrow that goes back and forth, that means it doesn't come apart 100%. That means it only makes some products. It doesn't make a lot of products. It only makes 1% products. So that means that 99% of this reaction stays right here. Where when you see the arrow here that only goes one way, 100% of it becomes product. So that's the difference between the double arrow and the arrow that goes one way. So if it goes one way, it means it makes all products. If it goes both ways, it means it only makes a little bit of products. So the arrow that goes this way, this means strong. If it goes both ways, that means weak. That's how you can tell the difference. You do not need to memorize them. You'll just look at the arrows to be able to figure that out. Same thing goes with bases, by the way. This is strong acid or strong base. This is weak acid or weak base. So for bases, again, they end in OHs. So if you see it ended with an OH, it's a base. And again, when they come apart, this means strong. Because strong means one arrow means it's going to make 100% products. That's a strong base. Weak bases, same thing. Weak bases, you can tell it's weak because the arrow goes both ways. So strong one way, weak goes both ways. Okay, so that's just a little bit of our acids and bases. We're going to talk a lot more about these at the end of the semester. Okay, our last double displacement, which is a lab that we're also going to be doing, is what happens when we have a metal carbonate. So a metal carbonate plus an acid makes salt, CO2, and water. So when we look at this, you're going to see this is actually a double displacement reaction. It's just like an extra double displacement reaction. That's what I would explain this. And so here's another example. So whenever you have a carbonate, whenever you see a carbonate here with an acid, that's your hint that this is what's going to happen. So a metal carbonate, so any metal plus a carbonate plus any acid starts with an H, has a metal here, is always going to make an ionic compound plus CO2 plus water. So what we have happening here is we have, if we write our double displacement reaction, oops, I'm going to show you this works. So if you have HCl plus Na2CO3, if we have the first one first and the first one stays first, H stays first and Na stays first, the two just switch places, HCO3 plus NaCl. And again, we have to balance that because it's a charge. So what happens in this gas forming reaction is this H2CO3 breaks up into water and CO2 gas. Did you ever make the little volcanoes when you were a kid with the baking soda and vinegar? No? Well, we'll do that. It'll be fun. You'll see. And so this is exactly what happens. It makes bubbles. So baking soda is a base, vinegar is an acid plus a metal carbonate. It always does this. So when this comes apart, so this is no longer here. So we've got salt, water, and CO2. And so we'll see bubbles in the case of this reaction. Okay. So let's practice this one. So calcium carbonate plus plus HCl. So remember, it's going to make our ionic compound plus CO2 plus water is what we're going to make. So if we have calcium, let's do it here. So if we have calcium carbonate, what's the charge on carbonate? Polyatomic ions, 2 minus. So we need CaCO3. Calcium's +2, carbonate's -2, so we're good. Plus hydrochloric acid. Remember, hydrochloric acid is HCl. So if we do this just as a double displacement reaction, remember, whoever's first stays first. So Ca stays first and H stays first. The second two switch places. So Ca goes with Cl and H goes with CO3. But are these charges balanced? What's the charge of calcium? +2, chloride's a -1. So to make these charges balance, what do we need to do? Put a 2 here. Hydrogen's +1, carbonate's -2. To make them balance, we need to put a 2 here. Okay, so now I want you to finish this reaction. It's not done yet, because remember, this is going to further decompose. So finish this reaction, then we'll go through it in just a second. H2CO3 is going to break down into water, liquid, and CO2 gas. So our overall reaction So we start with H2CO3 and it breaks down into water and CO2 gas. So this is our overall reaction. And again, this would be called the molecular equation. We could further break this down and do complete ionic and net ionic with this one also. So with any reaction we do, we can do complete and net ionic. Single, double, all of those could be done with it, and gas forming. Okay. Questions on this one. So whenever we see a double displacement reaction and you see this carbonic acid, the carbonic acid will always break down into water and CO2. So when you see that carbonic acid as a product of a double displacement reaction, it always further breaks down. So that's the key to see. Carbonic acid, H2CO3, will always break down into water and CO2. Okay, let's do a quick check. Both precipitation reactions and acid-base reactions can also be classified as, so precipitation and acid-base reaction can also be classified as synthesis reactions? No. Decomposition reactions? No. Single displacement reactions? So precipitation and acid base, nope, double displacement. So double displacement reactions, remember, can be precipitation reactions or acid base reactions and the gas forming reactions. Those are all types of double displacement reactions. Actually kind of cool. Okay, our last reaction type, combustion reactions. So when we look at these combustion reactions, a combustion reaction is anything that reacts with oxygen and heat. And a combustion reaction always makes an oxide of the compound and water. Well, when we look at CO2, when we look at a carbon reaction, it always makes an oxide of it and water. So a CH compound, for example, this one right here, do you see how we have CHs and oxygen? It always makes CO2 and water every single time. So whenever you hear combustion or burning or any of that sort, it's always going to be with oxygen, because if you think about a candle, if you put a top on a candle, what happens to the candle? It goes out because you have to have oxygen for something to burn. So whenever you see the word burning or combusting, one of the reactants has to be oxygen. Even if it doesn't say oxygen, it still has to have oxygen in it. So know that that is going to be a reactant. Now, if you have a hydrocarbon, now again, hydrocarbon, hydrogen and carbon. A hydrocarbon always makes CO2 and water. Okay, so that is the end of our reactions.